All right, in part one, we looked qualitatively at the implication for time of the constancy of speed of light, and what we discovered was that t0 cannot possibly be the same number as tv. In other words, the two observers are going to measure the time interval for that clock to tick, and they are not going to agree upon how long it took. In other words, the person on the platform, this person here, is going to look at the clock, and they're going to think that the clock is running slow. And of course, that's perfectly mirrorable. If there was a clock on the platform, the person in the carriage would look at the platform clock and think the platform clock is running slow. And it has to run slow because the distance is longer for the observer on the platform. And we looked at that qualitatively. What we're going to do right now is look at that quantitatively to see how much longer it is. The algebra gets a bit messy in this next bit. It's a little bit hard, but it's actually worth seeing that all of special relativity depends upon a very simple thing. Speed is distance divided by time, and Pythagoras' theorem. Okay, so here we are representing the path of the light beam. It has to travel down and back up again, and you can see it travels in a triangle. We're going to break that triangle into two parts. How far the train has moved on is going to be simply distance is speed times time. So the train's got some velocity v. It's going to happen in this time interval, which is tv, because we're measuring it from the perspective of the person on the platform. So we're breaking the two triangles. We can see that vtv on 2 is this length here, which we're going to call A. This one here is B, that's just L, and C is the hypotenuse. So C equals the square root of A squared plus B squared, that's Pythagoras' theorem. But the distance that the light ray is going to travel is going to be twice that, because it's got to go down and it's got to go back up again, and those two hypotenuses are equal. So it's going to be twice A squared plus B squared. Now, the distance that the light ray is going to travel, just remember that speed is distance over time. From the light beam's point of view, the distance it's going to travel, the distance is going to be the speed of light times tv. So what we can say is that this distance here, that's the same as that distance there. So we end up with c tv equals 2, the square root of a squared plus b squared. Okay. So this is where we're going to start. We just need to put in our a squareds and our b squareds. So c tv equals 2. Well, we're going to bring that 2 inside the square root side in our next go. So a squared is vtv on 2 all squared plus l squared. Okay, so I'm just going to grind through this algebra and see what comes of it. I want to take, let's just move everything across to the middle over here so we can kind of start again. I want to move that 2 inside the bracket, so c tv is going to be equal to the square root of 4 outside of vtv on 2 all squared plus l squared, which is going to give me 4l squared plus vtv all squared. B squared tv squared is going to be c tv, and all of that, we're taking the square root of all of that, so let's square both sides. C squared tv squared equals 4l squared plus b squared tv squared. Okay, let's keep working our way through this one here. Let's take this term over to the other side, so we've got c squared tv squared minus v squared tv squared equals 4l squared. Let's take out the common factor of t v squared outside of c squared minus v squared equals 4l squared. Let's just keep going with this one. So let's get our t v all squared equals 4l squared divided by c squared minus v squared. Okay, this is where it gets a little bit weird. We're going to take out c as a common factor of that denominator. So bear with me. Is 4l squared divided by c squared outside of 1 minus v squared on c squared. Okay, so we're getting there. So we're taking out that common factor. So let's take the square root of both sides to get rid of all the squares. So that gives us that tv equals 2l on c outside of the square root of 1 minus v squared on c squared. Okay, so we're getting very, very close. Now, if you remember back, how long did the event take from the point of view of the person in the carriage? Well, it was simply 2L on C, if you remember that. And if you have a look at it, 2L on C is our factor, common factor out here. So we can replace that with a T0, so we can say that TV equals T0 all on the square root of 1 minus B squared on C squared. And lo and behold, we can now say qualitatively how much time is going to be slowed down by. And time is going to be slowed down by this factor here. Now that factor there is very small, it's very close to 1 when our speeds are garden variety speeds. Even a fast jet, the speed is so tiny compared to the speed of light that that factor becomes insignificant. In other words, we agree upon the time. But when we approach the speed of light, we can see that we disagree on the time, and we disagree more intensely depending upon how close we get to the speed of light.